kind of off topic, but so I'm reading one of these papers, results from from Atlas, and they say we're measuring whether the C quarks, the CSEA quarks for S, for the strange quark, are symmetric in SU3. What does that mean when you say like sets of particles are symmetric, or they're like in a group like that?
Okay, I'm not sure what they mean, but what I would say is that I would normally use the term colorless or invariant under an SU3 transformation.
Okay.
At least if they're talking about SU3 of color, which presumably they are.
Like the state describing the quark is invariant.
So the idea would be you've got some C quarks that are SS bar. Are they colorless states of SS bar? In other words, are they invariant under color transformations? And one example of that would be a state that would be red bar plus blue bar plus green bar. That linear combination, which I think, I'm pretty sure is a singlet under an SU3 transformation.
That makes more sense.
Huh?
That makes more sense.
Okay, so last time we were talking about using the Feynman propagator to get to evaluate 2-point functions. Well, it is a 2-point function. To evaluate 4-point functions, and we did it for the case where we were neglecting interactions. Now we want to put the interactions in, and so we're going to say that L is, in Schwartz's notation, and as I said, remember I was bothered by a minus sign last time. Normally this would come in with a minus sign, so the Hamiltonian, in the Hamiltonian would come in with a plus sign, but since it's 5 cubed, you don't really care, and you might as well have it with a plus sign because it'll make the equations a little bit simpler. I mean, there'll be one fewer minus signs. Now we've seen that delta 1, 2 is I box, or box 1, on phi 1, phi 2. Phi 1, phi 2 means the mean value in the vacuum of the time-ordered product of phi of x1, phi of x2. And what happens is when box hits this, you get minus I times the delta function. I times minus I gives you 1. And so we start off the way we did it before. We say phi 1, phi 2 is I integral d4 of x, the Feynman propagator dx1, box x, phi x, phi 2. Well, we've skipped a line here. The line we skipped was that this is equal to I integral d4 of x delta x 1 phi x phi 2, and delta x1 is, no, there's no I here. Delta x1 is I integral d4 of x box wait a second, something is screwy here.
I in the definition of phi 1, phi 2. So the I gets out when you introduce the
All right, yeah, this is, let me just fiddle with it my way. So this is equal to, that's right. There are two, there's an extra D, yeah, sorry. So this thing here is I box phi x1. So I box phi x1 is delta x1, and delta x1 on that gives you this. On the other hand, and then we wanted also phi x, phi 2. I'm sorry, phi x, well now I've gotten this thing backwards. No, this is a 1. And now if we integrate by parts, we get that, yeah. Because then this is I d4 of x phi 1 box on phi x phi 2. So that's the top line. And where this is equal to that. Okay. All right, anyway, so let's go back to what was the top line in my notes. We've already expressed phi x phi 2. We had a previous expression for that, so if we go back and use that, we have d1x, and so this can be box x phi x phi 2. Well, this is just when you move the box through the time-ordered product, you move it through, but then you have a contact term that you need to subtract out. So it looks like that. On the other hand, box X, according to the field equations of box X equals this, which is, or rather, the partial of L, partial P, which is G over 2 phi squared. And so this is equal to I integral d4 of x, d1x, mean value in the vacuum, the time-ordered product of G over 2 phi x squared phi 2 minus I delta x2. All right, so once again, we use this counterintuitive trick that the delta function is I times box on the Feynman propagator. And we're going to integrate by parts, and so we get phi 1, phi 2 is d12 plus, and the d12 comes from this contact term, and then the next term is I G over 2 integral d4 of x, and we have the d1x, and then we have phi x squared phi 2. Okay, now we're going to use this trick and write this as d12 plus I G over 2 integral d4x. d1x and dx1 are the same, and then we're going to write this as integral d fourth y delta 2y phi x squared and then phi y. And then we're going to write delta 2y in this form, and so altogether we get d12. This is going to kick out an extra I, and so we're going to get minus g over 2 integral d fourth x d fourth y dx1 box y dy2 phi x squared phi y. All right, and the next step then is actually the next line in my notes is exactly the same as this. So oh, wait a minute. There's a box somewhere. Oh, the box. Yeah, this D and the box are starting to look a great deal the same, very similar here. Yeah, that was box y, not dy. And we can integrate by parts, and we go this way. And so the next line is actually d12 minus g over 2 d fourth x d fourth y dx1 dy2 box y on phi x squared phi y. Okay, on the other hand, we know how to move a box through a time-ordered product. It floats through and gives us also a contact term. And so let's write that down explicitly. Box y, phi x squared phi y, and this, of course, is time-ordered product. Well, when it floats through and hits this, we use this expression. And so this is equal to phi x squared g over 2 phi y squared. And then when it goes through, it hits the phi x twice. Or to put it differently, the second derivative with respect to ty hits delta of ty minus tx twice. And so what you get is minus 2I. There's an h bar, but I'm going to leave that out. Or just set it equal to 1. dyx, and what's left is just phi x. And so altogether, if I just use the fact that that's phi x, phi 1, phi 2 there, this is d12 minus g over 2 integral d fourth x, d fourth y, dx1, dy2, phi x squared g over 2 phi y squared minus 2I delta y x phi x. And if we expand that out, that's d12 minus the two g's here give us g squared over 4 integral d fourth x, d fourth y, phi x squared, phi y squared, plus ig d fourth x, d1x, d2x, phi x. Okay. Yeah, there was delta yx there. Okay. So, we're only, by the way, there are easier ways to do the things we're doing now. And I'm a little puzzled as to why Schwartz went through this at all. Since it was there, I thought I'd go through it. We're working, though, in perturbation theory to order g squared, so we can use the free field expression for this. We don't need to have any more, we don't want any more g's. And we've already computed that. In fact, that was what we did on Monday. So this is phi x squared, phi y squared, then the lowest order is dxx dyyy plus 2d squared xy, where g equals 0. And over here, we have a phi x. Well, we might want this to order g, but we don't want it to any higher. We don't need it to any higher order for sure. And so this then is phi x is d fourth y delta xy phi y, and this is d fourth y pi box y dxy phi y. We integrate the box by parts, and we get I d fourth y dxy g over 2 by y squared. And so that's the answer for that expression. Phi y squared is effectively dyyy. So another way of writing this is I g over 2 d fourth y dxy dyyy. Any questions? I'm not in love with this way of doing things. Just sort of realize that. All right, so we finally have phi 1, phi 2 as d12. That's the free field version, just the Feynman propagator. Minus d squared over 4 integral d fourth x d fourth y dx1 d2y phi x squared phi y squared plus ig d fourth x d1x d2x phi x. And that's d12 minus d squared over 4 d fourth x d fourth y dx1 d2y. And substituting in, we get 2d squared dxy squared plus dxx dyyy plus ig d4x d1x d2x plus, no, times, sorry, times ig over 2 d4th y dxy dyyy. All right, so the final expression, d12, it is d12, that's the free field version, minus g squared integral d fourth x d fourth y, a half d1x dxy squared dy2 plus a quarter d1x dxx dyyy dy2 plus a half d1x d2x dxy dyyy. Okay, so that's the end of it. And people who like to write diagrams would write this as 1, 2 plus 1 x y2 plus 1x loop y loop 2 plus 1x 2 y and a loop. All right. And we have to integrate over x. So, yeah.
So, no thank you. So we usually interpret the lines between points like 1 and 2 as some kind of interaction, right? So how do you interpret a loop then?
Oh, it's
Right,
the
but
thing
this is-
interacting with itself.
Is that a sensible? I mean, clearly it just comes from the calculation itself,
Yeah.
but how do you make sense of that physically?
Well, you know, if an electron can throw out a photon to another electron, it can throw out a photon that it catches itself.
You know?
So actually, sorry, it turns out that in QED that actually can't happen, now that I think about it, because the basic vertex is psi A psi bar. So you can have, in other words, QED is simpler in a sense. So you've got, this is your basic, this is your only vertex in QED. And so what you can have is you can have this sort of thing. But you can't have the thing double back on itself. And that's because the fermion field is quadratic in the interaction. The interaction has the fermions quadratic, the photons linear. So the closest you get to this sort of stuff is that. But on the other hand, if you just have a single scalar field and you decide your interaction is phi cubed, then your basic vertex is that. And then this guy can just come around like that. Whereas the photon can't do that. All right, a word about these diagrams. You notice we used G, we took as the interaction not G, but G over 3 factorial. That's so that when you differentiate phi, it was G phi cubed, 3 factorial. So when you differentiate, you go to G squared over 2, and if you differentiate again, you just get G. And if you have a quartic interaction, you typically have that over 4 factorial. And then this goes down to lambda phi cubed over 3 factorial and so forth. So these extra factorials, it turns out, tend to cancel when you work out your Feynman diagrams. And so that's why they're put in. On the other hand, you have to be careful. You can't just assume they're going to go away. You have to look at what diagram you're calculating. And frankly, my view is, instead of trying to learn a very complicated general rule that tells you how to handle every situation, just do the calculation in the theory that you're dealing with, and you'll discover how to treat the factorials and the combinatorics. And then, if it turns out that you're working on that theory night and day for a couple of weeks because, you know, that's your thesis or something, then after a couple of days it becomes second nature how to deal with the factorials. So that's my view. Okay, any other questions? Yeah,
What does it mean when these lines don't connect? There's that thing.
I'm sorry, give me that again.
What does it mean when the lines don't connect, when one doesn't ever touch two, when like it's, one is
You
never...
mean this thing here?
Yeah, one's never
It's
interacting.
called disconnected. And the fact is, we'll be ignoring disconnected diagrams. They actually have they play a role, and the only serious description I've ever seen of them is in Weinberg. And as I've said to you many times, if you're confused by something and you really want to understand it, and you have some time, go to Weinberg, volume 1 or 2 or 3. On the other hand, he's also written a book on quantum mechanics, which may be of interest to the people doing quantum information theory, I should think. He has a couple of chapters where he basically asks himself, what does quantum mechanics mean? And I think his answer is nobody knows. Or he says there are certain problems in quantum mechanics, and he illustrates them, and he describes a bunch of problems, and he said, well, this one really isn't, that one really isn't a problem, but on the other hand, these ones are sort of problems.
Is that a new book?
Anyway, so I recommend it to you if you really want to know something, then Weinberg's a place. Okay. The next topic is something that Dyson did in 1949. So first of all, let's remember what the Heisenberg equation of motion is for any operator we imagine, and this is a basic property of quantum mechanics, that time evolves because of the Hamiltonian, or the Hamiltonian is a generator of time translations. Momentum operator generates spatial translations. And so what we expect is that phi of t, of x and t is, now I'm just wondering, for some reason Schwartz uses t0 instead of 0. Most people just take for granted that time 0 will be the time where we have the Heisenberg picture and the Schrodinger picture and the interaction picture all equal. And on the other hand, Schwartz takes t0. That makes all the equations a little bit more complicated. Do you think you'd rather have me set t0 equal to 0? Okay, all right. On the other hand, my notes have the t0, so let's just, all right, so let me just do it then. Okay, so we'll assume t0 is 0. And what time that was, I don't know. Anyway. Okay, so that's the integral form of this expression. Here we're talking about phi, we say phi is the Heisenberg field, it's a fully interacting field. And we're going to be writing that as S dagger, we can write this as S dagger of t and 0, phi of x and 0, S of t and 0. Where we've written, we're using this notation of S of t and 0 is just e to the minus I h t. So that's just the time evolution. All right, now the differential equation that this satisfies, of course, is I s dot is hs. Now, in general, if you're doing fundamental physics, you assume that the Hamiltonian has no use by date, there's no t in it, there's no t dependence. and consequently this is the form for it, and which is what I assumed here. If for some reason you have a time-dependent Hamiltonian, such as you might have an external current in there that's time-dependent, then you would want to have this to be a time-ordered product of an exponential of an integral. So in other words, the more general description of this would be time-ordered product e to the minus I integral up to t from 0 h of t prime dt prime. But I don't know. I think that's kind of gilding the lily. Actually, let me tell you a quick joke that I got from some dentist that I once had work on my miserable teeth. And he said that at some point he had an elderly, wealthy woman as a patient. And she came into him on the first day and said, I want you to cap, oh, I forgot to tell you her name. Her name was Lily. And she said to him, I don't want to screw around. Well, no, she probably didn't talk like that. She probably said, I want all my teeth capped in gold. Why in God's name she'd want that? I didn't know. And he said, or he thought, I'm not sure which he did, but that this would be gilding the lily. Those of you who are foreign born, we have an expression in English for doing something that's fancy but absurd, and that's to take a lily that's perfectly lovely, white flower, and get gold, what is it, gold paint or something?
Yeah.
Paint, liquid gold, and paint the lily, and then you've got it. Of course, it would look terrible because you do a silly job with the paint. Or what happened, whether she got her teeth capped or not, I don't know. I just laughed instead of asking him what happened. I was dreading what he was going to do to me, so. All right, so much for that. Now, that's the Heisenberg picture. In the Schrodinger picture, of course, the thing is the opposite. In the Schrodinger picture, we imagine the operators as constant. We let the states evolve with time. And of course, the way we arrange that so that we get the same thing is that we have some psi prime phi x t phi, say. This would be, since this goes this way, it would be psi prime e to the I h t phi of x0 e to the minus I h t phi. Okay, so when you're looking up here, let's see, it's a matter of parentheses, okay? This is the thing that we want to calculate. We can write it in two different ways. If you put the parentheses here, you're in the Heisenberg picture. If you put the parentheses there, you're in the Schrodinger picture. And so it's just a matter of punctuation. Now, so that's going from the Heisenberg picture to the Schrodinger picture. Now, it turns out to be convenient to do something else, which is called the interaction picture. And in the interaction picture, what you do is you say that you want to keep the time dependence of the, you want to put some of the time dependence in the fields and leave and then you leave the rest of the time dependence on the states. And the idea is that that free fields, we understand free fields pretty well. That's what the Feynman propagator was. It was a vacuum, mean value in the free vacuum of the time ordered product of two free fields. And so the idea is let the fields have the free field time dependence, and whatever else there is acts on the states. Okay. So now let's go to this interaction picture. And in the interaction picture, and first of all, we want the Hamiltonian, which would be H0 plus V. This would be in the Schrodinger picture. In the Heisenberg picture, it would be, this would be time independent, just because the Heisenberg, the Hamiltonian is what evolves. So you could put e to the minus I and ht and e to the plus I ht, but that would be gilding the lily. And so in the Heisenberg picture, this thing has time dependence, and that thing has time dependence, and that's a very complicated time dependence. So this is Schrodinger picture. Schrodinger picture, they're all independent of time, and I'm assuming there's no, there are no external currents, so we don't have unnecessary time dependence. Now, in the interaction picture, the operators acquire the free field time dependence, and so H is H0 independent of time plus V of t in the interaction picture. And so that's what we'll be dealing with. Now, the fields, the free field phi 0 of x and t, well, this is e to the I h0 of t, phi 0 of x and 0, e to the minus I h0 t. So this we can think of this either as a Heisenberg field in the free field theory, or the field in the interaction picture. And of course, this thing actually is the one that we've been talking about all along, d cubed p, 2 pi cubed, 2 omega p inside a square root, ap, e to the minus I px plus e dagger p, e to the I px. And this is the Lorentz inner product. So the time dependence of these a's goes into the space vector. In other words, we have a dots of p is 0 in the free field time dependence. And that's what we're going to have in the interaction picture. Okay, on the other hand, the Heisenberg field is phi of xt, which is e to the I ht, phi of x and 0, e to the minus I ht. On the other hand, well, letting all the fields be the same at time 0. So this is e to the I ht phi 0 of x and 0, e to the minus I ht. So this is our picture that this is the interacting field, is the same as the free field at time 0. And now we can invert this formula. In other words, we can say here that phi 0 of x and 0 is e to the minus I h0t phi 0 of x and t, e to the I h0t. So that just inverts this and gives us phi at time 0. And we can stick that in there. And then what we have is e to the I ht. Phi 0 at 0 we're writing as e to the minus I h0t. And then phi 0 of x and t. And then e to the I h0t, e to the minus I h. Okay. So that gives us the Heisenberg field at time t in terms of the free field at time t. Another way of writing that same expression to describe x and t is, so let me just make sure that I'm not writing anything extra here. All right, so we're going to introduce this notation. S dagger of t in 0, e to the minus I h 0 t by 0 of x and t, e to the I h 0 t, s of t in 0, where, didn't I introduce s already, did I? Yes, s is just e to the minus I h t. And so this thing here just turned into s of t in 0. Okay, and we're going to call this, in fact, u dagger of t in 0 by 0 of x and t, u of t in 0. And this u of t in 0 is e to the I h0 t s of t in 0, which is to say e to the I h0 t e to the minus I h t. Okay. Just make sure we've got all the signs right. Yeah, okay. So this is our expression for this, and right, okay. Now what is the time derivative of this? Well, if we multiply by I, remember we have this I fetish in the physics department. I d by dt, u of t in 0. Now this is actually simple. We're differentiating over here. The trick is, when you differentiate this factor, you can bring down the h0 wherever you want. To the left, to the right, be in the middle. And then when you differentiate this guy, the h can come down here, in the middle, or over there. All right. Right way. In other words, to make progress, they're all correct ways, is to bring both of them down in the middle between the two exponentials. And so then this gives us e to the I h0 t. Then you get 2i, so you get minus h0 plus h e to the minus I h t. Okay. But h minus h0 is v. So this is e to the I h0 t v e to the minus I h t. And in fact, in these expressions, we can imagine that h0 and h are time-independent operators. Okay. So now, what we've got is this expression, but we can make this, again, it's this business of taking a step backwards that sometimes helps. Now we see that this expression here is in fact u of t0. Okay. It's equal to that. And then we've got this funny thing in front. Well, we rewrite this way. E d by dt u of t in 0 is simply v of t u of t in 0. So what is this v? This is the v in the interaction picture. Now this is what I'm doing here is exactly the same as what you learned in quantum mechanics. second semester, I imagine.
Late second semester.
Late in any semester often means it wasn't quite learned.
Yep. That was sort of the intent of the statement.
Yeah, well, in fact, this business is actually, I think I tried to do it somewhat more simply than Schwartz, because you have that damn T0 everywhere, and that's just, well, I mean, it just, you know, makes everything more complicated. And also, he didn't seem to, frankly, in spots, he didn't seem to know what picture he was in.
Yeah, because it seems like things are factors of t, and then things aren't factors of t.
Functions of t, yeah,
Functions of
no,
t, yeah.
that's right, and I think his thing is a little bit confusing. All right, so what do we have here? We have a nice differential equation. I d by dt of u is v of t u, and v of t is just the interaction Hamiltonian potential. But, oh, this is a zero here. Oh, no, that's not a zero. It's a zero here. So this thing here is v of t. So this is v, time dependence of the free theory. And so that just means that v is some expression of the fields. Those fields then will have free field time dependence. And let me just indicate something there so that you may be puzzled by it, but let me just imagine. Here we have, what do we have? E to the I, h0t, and we have some integral, phi of x and 0, d cubed x, e to the minus I h0t. Okay, so this is, cubed. So I'm imagining, and I'm leaving out the coupling. So I'm imagining that, so this thing, from here to there, that's V in the Schrodinger picture. Now, we're acting on it with e to the IH0 and e to the minus IH0. Well, what happened? What happens is that this is an integral, e to the IH0t, phi of x and 0, e to the minus I h0t, e to the I h0t, phi of x and 0, e to the minus I h0t. I'm starting to lose track. E to the I h0t, phi of x and 0, e to the minus I h0t, d cubed x. So that's what we've got. And now you see that this is just phi of x and t. This is all phi 0. And so this is phi 0 of x and t. That one. This one gives us another phi 0 of x and t. And then this one gives us a third. So the whole thing is phi 0 of x and t cubed. So in other words, it's a unitary operator, e to the I h0t, and when you slap it on both sides, you can just sort of, and it acts on each individual field. Any question? Yes, do you want a candy?
No, thank you. So we started with just a phi in our original expression, and now we have a phi 0 on the other side of it.
Right.
I'm a little confused.
What we're imagining, I think, in this whole business is that at time 0, all the fields are the same. Time 0.
Well, free.
And then, well, free refers to time.
Right.
And if you're at one instant, then you don't know whether you're free or not, right?
That
In other
is
words-
in existence yet.
If the prisoner is in jail at time 0, is he free or not? Well, you find out at time t he's walked out the door, then he's free. But you don't know at time 0. Good question.
Thank you.
All right. Okay. So that's the picture. This is the differential equation. And the solution is kind of obvious. I mean, it's obvious after you know what the answer is. If you have this equation, I d by dt u of t0 is v of t u of t0, well, obviously the answer is u of t in 0 is a time-ordered product of e to the minus I integral 0 to t v of t prime dt prime. You see, because now if you take the time derivative, what does it tell you? Well, it's an exponential, so you differentiate the exponent. But what does this thing look like? It's got v of t prime for t prime close to t is way here on the left. So when you differentiate, the v comes down on the left-hand side. Or to put it differently, u of t plus dt, 0 minus u of t divided by dt, okay, is e to the minus I v of t dt u of t in 0 minus u of t in 0 divided by dt. And so this is, you expand this and you get 1 minus I v of t dt times u minus u over dt. The one term, 1u minus u is 0, and so this is minus I v of t times u. So that's why it's a solution. So, and this is basically why time ordering comes into physics. It's because in the interaction picture you want to have these this time dependence and so forth. Okay, now what does this exponential look like? Well, if we expand it, and this is perturbation theory, imagine v is small. Well, this is time-ordered product of 1 minus I integral v minus a half integral v, da 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 da, all time ordered. And so this is 1 minus I integral 0 to t v of t prime dt prime minus a half integral 0 to t v of t prime integral 0 to t v of t double prime. Now these have to be time ordered. dt prime, dt double prime, and then higher order terms. So it's and what you get in general is minus 1 over, well, not minus. What you get in general is minus I to the n over n factorial, an integral from 0 to t n times the time-ordered product of the interaction Hamiltonian in the interaction picture, which is to say the interaction Hamiltonian with the free field time dependence, and then you integrate over all the times, but you preserve the time ordering. For some reason, Schwartz then repeats this thing for the case of, he imagines doing it in terms of perturbation theory. There is one little trick there that So maybe I should do it. All right.
Actually, can I ask a question before you move on?
What?
Can I ask a question before you move on?
Yes, of course you may ask me a question.
Okay. So, you say that we just need to do this time ordering. How exactly does one do that?
Carefully.
Because I was thinking you could just sort of adjust the limits of the integration variables in just the right way, then they only increment, you know, in the correct order. But the way you've written it, that doesn't look like what you intended.
Here, okay, yeah, all right, this is a good point. This is, actually, it's an excellent point. And in fact, let me do this. I want to do something here. I lost track. Oh, never mind that. Suppose, let's reformulate this. This thing is minus a half. Let us do this. Let us integrate 0 to t dt prime b of t prime, and now integrate 0 to t prime b of t double prime dt double prime, okay? Now, well, I need to correct that factor, because here, you see, we had a square. If this is t and that's t prime and that's t double prime, here we did the whole square, but we time ordered the v's. Here, we're just integrating over the case where t prime is greater than t. So in other words, we're integrating over this part. So we're integrating over only half of the space. So we have to write, we multiply by 2. So in other words, if you want to write it that way, you need to multiply by 2. All right, I think that that's enough of that. Schwartz introduces something, I'll just explain it rather than go on and on about it, because I'm not sure this is what I don't know if we really need it. All right, so I was talking about u of t0 all the time. We can generalize that to u of t1, t2 as time ordered product e to the minus I integral t1 to t2 v of t prime dt prime. Okay, now, that's fine for, well, let me see, I'm sorry, let me T1 up here, T2. And we're imagining here, we're typically imagining that T1 is greater than T2. Now, Schwartz generalizes this in a funny kind of way. What if T1 is less than T2, then he writes the same formula, but he kind of gives it a different meaning. So it's a e to the minus I integral. Now it is the second one is T1. Oh, it's the same thing, T1, T2, B of T prime, dt prime. All right, but now he does the time ordering with 1's that are T2 go on the right, if they're closer to T2, and on the left, they go on the left if they're closer to T1, whether T1 is less, even when T1 is less than T2. But in that case, the dt is negative. Okay. So what he gets here then is that this is e to the I dt v of t1 dot 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 e to the I dt v of t2. This is for the case in which t1 is less than t2. So now if you multiply that from the left by, in other words, if you have u of t2 t1, u of t1 t2, where t2 is greater than t1, then this thing is e to the minus I dt v of, I'll just write it as v of 2, dot 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 e to the minus I, well, what the hell, t2, minus I dt v of t1, you see, and now you have u of t1, t2 interpreted in this sort of generalized way, you can see that you get 1. Now, why this might be necessary, I don't know, but that's for some reason what Schwartz did. I'm not quite clear as to why that's the case. All right, the next thing, and this is important, and it's a little bit confusing, and I think there are some typos which Schwartz actually has on his typo pages. Let me try to get this straight now. We first of all have A of some momentum at time 0, an arbitrary h0 here. Well, this is certainly true because at time 0, the annihilation operator is the free field annihilation operator, and it annihilates the free field vacuum. Okay. On the other hand, we imagine that AP of 0, if we time evolve it back that it annihilates the interaction picture, not the interaction, it annihilates the full vacuum at negative times. And so we are right. In other words, let me rewrite this. This is e to the IHT AP of 0. Actually, I think I got a sign wrong here. No, it's okay. I've got the sign right. So this is AP of T on the vacuum. Now, what is it? Well, the limit of this as T goes to minus infinity should be 0. In other words, this is now the interacting annihilation operator. At minus infinity, it should annihilate the vacuum. And we may be thinking of two different kinds of vacua here. and I think Weinberg actually makes this distinction. We're thinking of this as the in vacuum, so to speak, and the other one is the out vacuum. All right. So, since what we've got then is basically AP of 0, e to the minus I, H0 of t, any old t, 0 is 0. And then we can cancel this factor, which is just a unitary factor. We can AP of 0, e, and now this is e to the really, t goes to minus infinity, so this is I, H, big T on 0 is 0. Okay. So now what we can say is that these two states, since they're annihilated by all of the annihilation operators, all momenta, these two states must be essentially the same. All right. And so that tells us then that omega is equal to e to the minus I h big T e to the minus I h 0, and now this is any old t, so let me just put t there, because that's a flexible t. And this is proportionality, there might be overall constants there.
Where did the big T come from? It's on the bottom, but what was it?
Where does what?
The big T, capital T.
Big T means,
Just some huge T, okay. That's it, yeah.
and the idea here is that I'm taking this time to be minus infinity, essentially. And if little t becomes minus big T, then we have e to the IH big T. So this is the idea that omega, the physical vacuum, or at least the in vacuum, is some constant n in, and now it's a limit. You can either have t goes to minus infinity, or we just have big T. In any event, it is, I'll write it in two different ways. Lim t goes to minus infinity, e to the iht, e to the minus I h0t on 0. Okay. And this thing here is ni lim s dagger of t and 0, e to the minus I 0t 0. And another way of writing it is ni u of 0 minus infinity. And that's because, well, it's just because of the way we define things. I don't know if I need to go back and forth. In other words, what we've got is s dagger of t, 0, e to the minus I h0t is u dagger of t0, and u dagger of t0 is u of 0t. And so that's one. So in other words, this thing here was actually, let me put in another equation. Ni lim, and this is u of minus infinity 0. No, u dagger. U dagger minus infinity to 0, and that's the same thing as u of 0 minus infinity. And I suppose that's why he did this funny business here. Okay, similarly, you can say that the out physical vacuum is some final state constant times 0 u infinity 0. Understood in the limits. All right, so now what we've got is actually quite nice, and let me see if I can, so I'm going to skip to this board here, or maybe what I'll do, well, I'm wondering, maybe I'll just erase this board and hope that the New Mexico weather will dry this in time. All right, now let's go over here and start the derivation. This is actually just putting together what we already know, and most of it is straightforward. It's a matter of kind of bookkeeping. Okay. So let's suppose T1 is later than T2, dot, dot, later than Tn. Frankly, I normally think of it backwards. I normally think of T2 as later than T1, but he wants to do it this way, so we'll humor him. Oh hell, I've got too much water on the chalk. All right, physical vacuum, time-ordered product, fields, and these are Heisenberg fields, x1, x2, phi of xn. But we chose a particular time ordering. So this is omega just phi of x1, dot, 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 phi of x1. Now, we've got this relation that omega is nf that. So this is nf, vacuum of the free theory, u infinity 0. And now we can write phi of x1 as u01 phi 0 of x1. So in other words, this thing takes this operator, and then we're going to have u 1, 0, because remember u1, 0 is the adjoint of u0, 1. So this unitary operator takes the free field at time 1 back to time 0. At time 0, it's the same as the interacting field. The next one is u02 phi 0 x2 u20. So once again, this takes the free field at time t2 back to the free field at time 0, where it's the same thing as the interacting field. Okay. This is somewhat counterintuitive. All right. Dot, dot, dot. u0n, phi 0 xn, un0, u0 minus infinity, 0, and here I'm using an ni. So I'm using the full vacuum is ni times u0 minus infinity. Right, okay. All right, now these 0 things, this just becomes u12. Right, we've seen that these things work out that way. So this is u12. This thing, so this is nf ni 0 u infinity 1, and then this is phi 0 of x1, u12 phi 0 x2, and this then becomes u23 dot 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 un minus 1 n phi 0 xn, and then u n minus infinity, because that was n 0, 0 minus infinity, that's n minus infinity on 0. Okay. Now if we look at it, we see that everything's time ordered in here. It's plus infinity 1, 1 is greater than 2, 2 is greater than 3, blah, blah, blah. All right. So, to save time, I'm just going to toss in a time ordering. And once I toss in the time ordering, I can screw around a little bit. And I can take this thing here and go back to infinity 0, 0, 1, and take the infinity 0 over to here. So we get u infinity 0, u 0 minus infinity 0, and then this one was u, and well, I'll make that u in 0 again. All right. So now what we've got is that this thing here is those proportionality factors 0, t, phi 0 x1 dot 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 phi 0 xn, and u infinity minus infinity 0. Oh my God, I'm over time already. Let's just say we get a very nice expression when we finish this. It's in Schwartz there. I will pick up at this point on Monday, and so the homework is on the web and it's due a week from today. And you want me to give you the solution to the